Okay, hello everyone. Welcome after the break. So this time we are going to talk about distributed computing, and this presentation consists of two parts. Firstly, I'm going to make a hopefully short introduction to some basics of this of parallel and distributed computing in Julia. And then at the next part, Julian is going to discuss Dagger.jl, which is a great abstraction layer for distributed computing and scaling out computations, especially those computations that are represented as set of dependencies that can be represented as a directed acyclic graph, which is DAG, and that's why the name Dagger. Okay, so let's get things rolling. So my introduction to distributed computing will be kind of fast. So in computers, we have many ways to scale out computations, and everything on this list is supported by Julia. Although we'll not be discussing everything today due to the lack of time. There are also some you can also find background slides in the course materials, but what options we have? So one kind of parallelizing stuff is the single instruction multiple data feature of Intel processors, and this is supported by Julia. So you can tell the Julia compiler to compile such code that several operations are happening simultaneously. A good example here would be writing you some custom function for dot product. And you can easily parallelize this using SIMD, or maybe if you have some your own routines for matrix multiplication, then in Julia code, thanks to SIMD support, the Julia native Julia libraries can be as fast as C. The second option are green threads, also called coroutines. And this is the kind of parallelization. I could call it pseudo parallelization because we are still within a single within a single thread or our machine. But what we can get is that this thread is kind of shared or is behaving like multi-threaded environment when you need to yield, when you need to wait for other processes. So a good example is I/O. So if you, for example, are writing a web scrapers, most time you are waiting for the network. So if you write a web scraper, you could use this technique to parallelize such thing. Now, the next thing is multi-threading, and the Julia is supporting a correct multi-threaded mechanism in contrary to Python, which is quite not working due to global interpreter lock, although some job is done in that direction Python. So in Julia, we have native support for multi-threading. It is also worth noting that some part of support have support in language, but also Julia can call some libraries which have inbuilt multi-threaded mechanism. This affects, for example, for linear algebra libraries, and sometimes for like BLAS libraries, you can independently control the number of threads regardless of Julia configuration. I will not be talking about this small issue, but if you are doing lots of algebra, then during the break or so we can also discuss it. So, and then we have multiprocessing. So basically, we can run at the same time several processes working together as a Julia cluster. And Julia is providing very nice abstraction for multiprocessing because kind of from implementation perspective, it does not matter if it occurs on a single machine or a cluster across network. Of course, you need to perform different optimization tasks and so on, but Julia has very nice unified API that you can do both. Last but not least is GPU computing. This is not something we're going to discuss today, but it's worth noting that you can also use Julia to perform computations on GPU accelerators. Okay, so these are the options we are going to discuss. So we have threading. Threading is a single process, and it's kind of cheap because we are within single process. It's easy to spawn a separate threads. All threads are sharing the same amount of memory. Now in Julia, the number of threads running simultaneously is limited by the number of processors. So you configure what is the maximum number of threads for when starting a Julia process. Since several threads are reaching the same memory space, it can lead to some tricky issues such as locking or false sharing. Now, the next option is multiprocessing. And then for multiprocessing, we have multiple processes. Each of those processes has independent piece of memory, and they can run simultaneously regardless of cluster size. What is difficult? Inter-process communication is difficult, and so it's not so easy to send objects between processes, and it can make the life sometimes hard. But on the other hand, for example, the current Julia capability is perfect. For example, when you do grid computing, so you take a parameter space, and for a given parameter space, you are performing a parameter sweep over that space, and you want to collect results somewhere, perhaps into data frame. Now, multiprocessing in Julia is naturally being extended into distributed computing, because from the point of view of Julia's API, it doesn't matter if processes are on the same machine or they are on a distinct remote machine. Now, when you are running a Julia process, you can provide parameters when starting the process. So you could write, for example, Julia minus t, and then provide the number of threads. So Julia minus t and 4 would start Julia with 4 threads. The same about multiprocessing. Now, processes can be also dynamically added to a running Julia process, but you can do Julia minus p, and then a Julia cluster, a local Julia cluster gets started. You can also provide a machine file. So machine file consists a list of host IPs and the number of processes to spawn on each host. And then Julia is taking this machine. So this is just a text file. Then Julia takes this text file and performs an SSH connection to remote hosts and is spawning the Julia processes. In the background material, there are some notes on how to configure SSH for that, because we need then have a cluster which enables connection on passwordless SSH to build such Julia cluster. This is yet another story, but if somebody wants to build such cluster, let me know. I can send you also some more detailed materials. So we start with multi-threading. So we'll have an issue, we'll have a situation that several threads are using the same memory area. Now, the notebook for today, before running it, it should be noted that before you start Jupyter Notebook, in the Julia console, so if you have a Julia console, you should do, so in Julia console, you should do the command and Julia num threads equals 4. So when I spawn the Jupyter Notebook, it will start with 4 threads. The same as if you use Visual Studio Code. If you use Visual Studio Code in the Julia configuration, so let me go to Visual Studio Code configuration. So you have settings, and when you search for Julia settings, or maybe I should be able to write threads, then you have Julia num threads. Edit in settings.json, and then you find it Visual Studio Code. You have Julia num threads. So this would be the number of threads Julia started. So the multi-threading level for Julia is something that needs to be configured externally to the Julia process. You can do it both in Visual Studio Code, or you can set the environment variable. Of course, you can also set this environment variable in your system environment variables. But here's another thing. I just set the value n, and if you use Jupyter Notebook, this is being spawned as a child process of this Julia process. So this is going to inherit the system variable, and then we can have 4 threads. So if you've done it correctly, when you run the line here, number of threads that your Julia is running, it should be 4. So I will be using 4 threads for those examples. And I have been also talking with Julian, and he will be using 4 threads for his examples as well. Okay, so let me continue. So the first thing I'm going to do, I'm going to load packages. So benchmark tools is needed. Distributed, I'm going to use slightly later. So benchmark tools we'll be using for benchmarking of everything we do, and distributed is for parallel, for multiprocessing. This will be in a minute. So first, let's start with multi-threading. So I'm making sure that I have 4 threads running. So I have Julia running in 4 threads mode. Anyway, there is just a single Julia process running. So let's see how we can use multi-threading mechanism. Now, this will be like very introductory examples because more advanced will be presented by Julian, hopefully. Okay, so the first piece of code we have here, it's a very simple one. It's calculating a sum of all rows in a matrix. Okay, so it takes some matrix X, it calculates the size of the matrix, so number of rows and number of columns. It creates some place to store the result. Maybe it would be nicer to use like L type of X, so you have the same type. But here, just for benchmark, I assume the default is float 64, so I will be happy without providing. I just write zeros. But if you wanted some more generic code, you want add L type here maybe as well. Now, so I'm going through all columns and calculating sums. Easy as this. So this is the not parallelized version. And now if you have a loop like this, it turns out that it's all enough what is needed to do for the multi-threading of this code is to add threads at threads. Oh, and by the way, at inbounds is turning off bounds checking. So if you are sure that you are not going with your indices, if you are not going to run out of the bounds, you can, in Julia, you can turn on inbound checking. So this is very simple code. I'm also assuming that that this is just a standard matrix of floats. For production code, you should be make sure how the array is based index, because theoretically you can have different indexing in Julia than starting from 1. You should be also probably make sure what is the element type. But here I'm just focusing on the threaded part. So this code is as short as possible. So what I do here is thread at threads, and all it's doing is then multi-threading this loop. And now what's going to happen, the job for I from 1 to C, it's going to be slashed into the number of pieces equal to the number of threads. So I have 4 pieces. And there is one more interesting thing for noting. It has a parameter which is called schedule, and threads have few scheduling policies. I think it's in PMAP, those scheduling policies are being described. I'm not sure if it's going to show. Let's see if this I have in PMAP, the scheduling policy. Blah, blah, blah. They are not. Okay, so I'm just going to say that normally, so the problem in parallel loops, we have that the jobs can have different sizes. It's not here because here I'm just adding columns. So the scheduling mechanism by default is polling the job. So it's taking job by job. But you can have also other strategies, like, for example, assigning an equal amount of jobs to each thread. So I have 4 threads. I say, okay, I have 40 columns. So each thread gets exactly 10 columns. And for this strategy, this would be fine. But for other cases, probably not. Okay, so let me now run this. And so I have defined this function, and now we are comparing the performance. So I create some matrix. 1000 by 1000 by 10,000. So I have matrix with 10 million elements, and I'm calculating the time. So I'm running the code twice. The first run is the time, it includes also the time to compile the code. And we indeed are seeing this is the compilation time. So it takes a significant amount of time to compile this function and significant time of memory. But the second run, we can see it's for the non-parallelized code, it's 14 milliseconds. Now I run the multi-threaded version. And what can we observe? It takes roughly 3 times as long to compile this code, because obviously this is much more complicated code with much more of machine code. But then if I run it, if I run the compiled code, you can see it's like 5 milliseconds. So it's roughly 3 times faster. This is expected. You will never get the speed up equal to the number of threads you have. Like I'm using 4 threads, but it's not 4 times as speed. There are many reasons for that, including, for example, the thermal control rules for Intel CPUs, etc. But the speed up is very significant, so you can see that I've added just a small piece of information, and the code is fast as 3 times as fast. Okay, threading is creating lots of problems, and one of the problem is locking, and also this is why the need for development of parallel processing libraries such as Dagger. So assume that we have very simple code that is taking a value x and increasing its value 1 million times. So what's going to happen if I'm going to run it multi-threaded? So I took x and I'm increasing int value 10 million times, but I do it in parallel. If I run this code, I can see, so I do it 1 million times, but if I run this code, I can see that the value is 250,000. Why? Because increasing the value of x by 1 requires taking the value of x, then calculating the, increasing by 1, and then assigning it back. So this is more than one operation. And when one of the threads is taking the value, the other is assigning the new value and so on. And they are overwriting the same value all the same time. And then I'm not getting the number of increase of variables I would expect. Even worse, each time I'm getting totally different result. I'm not happy about this. Okay, so so there are many ways. There are many ways to do it. By the way, the function that it's just adding without multi-threading is not good for benchmarking, because the compiler would just slash it to returning the value 1 million, which is this example is about. I'm not showing that. Okay, so what we can do it? So we have few options. We can use atomic variables. So this is something implemented on the CPU level, and it's controlling the concurrency. So we have atomic add function. So this is one option to properly compute this, to declare this variable to be atomic. The other option is to use logs. And there are two logs type implemented by default in Julia. One is spin logs, and the other is reentrant logs. Basically, it's recommended to use reentrant logs. They are slower but much safer. They are much safer to use. And so you can see this is logging the part of code. So here I'm creating a log. And when the code is within a log, it can at any time it can be executed only by a single thread. Okay, so here I'm creating a version with spin log and reentrant log. Now I have all these pieces code. So what is appealing is to take all those functions. So I have this function that has beta implementation with atomic values, with spin logs, and with reentrant logs, and I'm running it several times to see what were the so I'm running it a few times to see what were the running times. And so these are so what you can observe, that the atomics in these examples, the atomics are the fastest, but they are most difficult to program. the spin logs like but this is of course very small piece of code, and usually in a parallelized loop you have much more code, and usually those times do not do not matter that usually those times do not matter that much. Okay, so you have those timings. Okay, so we did that, and we can see that reentrant logs have similar performance, but there are some, but basically they are the recommended way to go. Okay, I'm going quite quick on with this. So the next thing, in order to give floor to Julian to show Dagger, so the next thing we need to slightly be aware of is green threading. So green threading is basically doing something in parallel while releasing the main thread to do something else. So a good example would be function sleep. So the function sleep is sleeping for 2 seconds. And if I run it, you can see that I get a result after 2 seconds, which is expected. Now, what I could do, here I have a function that is sleeping for 4 seconds. So when I run this piece of code, I can see it will assign the result to t. If I run it, I can see that it got executed after 10 milliseconds, and t is representing a task. So it's a task that is running on site that is doing something. I'm waiting for that task. In the meantime, this task has completed. So if I query this task again, I can see it's not runnable, it's now done. Okay, so once again, first, if I run t, it's task runnable, but then once 4 seconds pass, I press Control Enter again, this task is done. So the next thing we have here is the it was some other example with waiting. Suppose I have some very simple function that is performing some job, and here, it could, for example, download a file from the internet. Here I'm just emulating downloading file from internet or any IO operation with sleeping, which makes the code simplest. But for example, let's assume this file is downloading a file from internet. This function is downloading a file from internet, and it can last anything for few to 10 seconds. So if I define a vector for results, okay, I used undef here, so I see whatever memory rubbish was there. So that's why it's quite ugly. If I run it just sequentially, it's going to finish by after something roughly around 4 seconds, and I see the results. Okay, so I see random numbers and those random values that got generated. So the idea is to use green threads for it, but if I just start it asynchronously, then what's going to happen? If I run this, it finishes immediately. So it finishes just after a few microseconds. Okay, but what you are seeing here, the results are totally wrong because I'm still seeing rubbish in the memory. I'm starting to wonder what happened, and maybe I would like to see the results. Okay, once again, if I now type result, then I'm going to notice I typed wrongly. If I type result now, then I'm okay. What happened? In the meantime, all those processes have completed, and now it's fine. The state of result is fine. So what I need to know what I need to do? I need to synchronize. I need to wait for all those processes running on site. So this is the API for it. So I have this result, and I'm synchronizing all asynchronous processes. So what's going to happen? I'm going to spawn several asynchronous tasks, and I'm going to wait for all of them complete. So this is how asynchronous processing works. Yes, this is dynamic. Yes, so the threads are also that. So for threads, we have also spawn. I have not been showing that because for scientific computing, I usually do loops, and for more complicated strategies of dependencies, probably Dagger is better. So if need to use spawn, probably it would be much easier. I guess Julian agrees should be much easier to do that in Dagger. So this will be shown by Julian. But here for at async, so async is very often used with combination of something. So I needed this concept of asynchronous jobs. It is, yes, it is dynamic, and it's all happening within a single thread. So threads, the module threads has all at async macro, which is creating a new thread. So it's also possible, and it's also possible to do it via a separate thread. But if you use it just without package name, this is just creating an asynchronous task, which is a green thread. So it's all like software emulated. So it's a software emulated threading, and it's not native. So anyway, it can do just one thing at a time. It just has a nice switching mechanism, and it's very lightweight and very fast. So the way it's ordered, now I think I have, now I run it from 1 to 9 and assigning in proper places. But would I have, so your question is, would I have the same ordering? I think it might not be. So if I use this to append to a vector, mm, yeah, I do not have, yes, I do not have the guarantee, but anyway, any async job would mutate this vector at a single point of time. So I do not have the issue of like locking because it's not real multi-threading. So I do not have the risk that two asyncs try to, mutate some, if they were started from the same thread, like here, because it's not multi-threading. So I do not have this locking problems. Two different locations. Yeah, this is of course, but even if it was same location and it's async, you will not destroy it because async is single threaded. It's just behaving like it was multi-threaded, but it's fine if the job is IO job. So reading a file from Amazon S3, you can use it to parallelize it. Making intensive matrix multiplication, no, because you need lots of CPU. So if you need lots of IO, use async. If you need lots of CPU for your job, now you need to go to multi-threading or multi-processing.
And just a point, the general recommendation is not to use that async unless you need it. You should use threads.add_spawn, which is the multi-threaded alternative, and use locking. That is generally what is now recommended. Just an aside.
Okay, so as Julian has said, the generally multi-threaded, I'm selling online for online audience, generally multi-threading is recommended. Although those green threads are much lighter, like if you need thousands of them, you wouldn't probably. I'm wondering how the performance if you would need lots of them though, but because you can, so they're very lightweight, so you can have plenty. Okay. So we have now the distributed module, and it works like this, that it creates a Julia cluster. So on my machine, as you can see, blah, 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 details, I'm running now something like 3 Julia processes. So maybe one is master and one is Jupyter notebook. So I'm now going what to do. I'm going to start a Julia cluster. And I start Julia cluster by doing add procs. So add_procs is adding processes to my Julia cluster. Now the API for this is very clever because those processes, by default, they are being added on my machine, but it is possible to provide such parameters that processes can be added from remote machines. Okay, so it has support for adding processes on remote machines. Also, there is a Julia package clustermanagers.gl, and you can, for example, add_procs can connect to high performance computing environments such as Slarm or Condor and request new or SGE, and then request new processes from say Slarm and add it to the Julia cluster. So the default version is just adding processes on the same local machine. But the very nice thing is it's a unified API for high performance computing environments. So you can test on your laptop and then you can go to a Cray supercomputer or a cluster at Amazon Cloud and the code is still the same. You just modify the @prox command. Okay, so I'm adding here 4 new processors to my Julia cluster, and what you can see now, I have 7 Julia processes. I had 3 and I have added 4, so it's a total of 8 Julia processes. I can see those processes. These are called workers and they are identified by number. So I have workers number 2, 3, 4 and 5. The worker number 1 is the master or the main worker. Okay, so this seems to work. So now we have some very simple parallelization scenarios. Now the more complex stuff will be taught by Julian in a few minutes. So this is a function that is just calculating of sum of 100 million numbers in 10,000 batches. And you can see this function takes like 0.7 seconds to run. Now I could parallelize this function. Okay, so I'm using distributed was loaded. So in order to distribute a piece of Julia code, you basically provide add distributed macro. So this is for loops. And like we had a talk with Julian before, this is probably the only scenario it works easy and well. It's quite tricky to get it working for more complicated scenarios. But the default distributed package has a really great distributed loop. Although it has one disadvantage, it does not do load balancing. So if the loop is from 1 to n, it's going to slash exactly into, here I have 4 processes, so exactly into 4 slices this job. And it is not able, contrary to thread.threads, is not able to move the jobs around processors if some of them finish earlier. Okay, so the disadvantage of this, you will wait. So from all those loop computations, you are waiting for the one that takes the longest time to complete. Okay, so this add distributed loop is not able to move the jobs around. Okay, but if I run it, what you can see, so you can see it takes long to compile. It took 2 seconds to compile. Basically, distributed code take a reasonable amount of time of compile. So the compile time overhead and for the larger clusters could be just even few seconds, just with the distributed package. So something to be aware of. But then I have roughly 4 times speed up. So we got here a very nice speed up of this process by just adding 4 workers to the Julia cluster. So these are my 4 workers, and they all participated in these computations. Now you can tell to do something on a specific worker, but maybe this is not a recommended approach, and I'm running out of time, so I'll skip that.
That's actually, you want to show that.
Okay, if you say, Julian, it will be useful, then okay, so I can execute a process on any worker, and if I execute something on a given worker, what I'm getting is a future object. And future object is representing a promise of execution something in the future. And if I get a future object to get the actual value from that, I need to fetch that. Okay, so this is residing on the remote worker. So this is working like this. And now there is one thing worth knowing. If you have functions, so say my ID is yielding the ID of the worker where function works. If you call this function like this, so it's executed on the worker number 1. But if I, for example, try to execute this function on a different worker, I get an error that it does not exist. So we need to manage the thing that each process has a separate state, each process has a separate memory, and each process has a separate function definition. So what is the solution? You have add everywhere keyword that is defining function or workers, and then you can be sure you can execute it. Okay. So the last thing I would like to show is what is the typical pattern for running distributed loops. So this is a template code for, basically this is a template code if you have some loop that you want to run across multiple processes. So what do you usually do? You usually have a package. So here maybe it does make like sense for this. And this pkg activate is kind of not useful because I'm not sure if I have a package at the folder I am now. But you activate the package. You load all the libraries you need on all of the workers, and perhaps your custom package as well. Then you might also define some function, usually define them across all cluster. You could define function on a specific worker, but it's difficult to manage. Then usually you have some function that is initializing worker state. Good example would be to have a different configuration of random number seed generator on each of the workers. Very often those computations can be kind of like Monte Carlo simulations or some data sampling and so on. So, and the default seed is the millisecond time of the clock, and the workers might be created at exactly the same millisecond, and you might end up having identical random number seeds across workers, which is usually you don't want to have. So this is a sample initialization function. And if initialization function is big, then what I would usually do, I would load them asynchronously. So this is a piece of code that is loading the initialization functions asynchronously. Okay, so this has run. And now this is the last thing, typical pattern for computations. So typical thing that at distributed is useful for are parameter sweep loops. So if you have a set of parameters you want to test for, like here I have a set of parameters for I and j, and for I the values are from 1 to 4, and from j the values are from 1 to 3, and I want to do a Cartesian product of both those values. This is very typical scenario. So this is called parameter sweep, usually in most of papers, and this is very typical scenario on what you want to do. Now, this is a good piece of code if the computational complexity of each job is kind of similar, because there is no load balancing. It will be cut into equal pieces. Each of the workers will get its job, and then it will be executed. I understand if you have load balancing, Dagger probably could help because it has some management of job queue. But here, no management of job queue, so it will be done in kind of a stupid way. So, but now if your jobs are equal, the pattern is very simple. You do your computations and just generating random functions, and there is this calc thing. And usually for my scientific computing projects, I try to collect data as a data frame. So what I'm doing here, I'm creating here a data frame having just a single row. But here I'm assigning an append function, and this append function is going to merge all those single row data frames into one big data frame. Now, please note there is no return function. So it's not allowed to put return here, but the last line is kind of returned for the loop. So this is kind of maybe not a natural API, but whatever is in the last line will get collected by the add distributed macro, and this macro is going to apply the function that is here. And if the job sizes are equal and you just do simple parameter sweep, this approach is very comfortable. For more, and what do you see? Okay, so what we see, we are getting a data frame as a result. And if you look here, it's worker ID. So those 3 results were calculated on the process 2, those were on process 3, and so on. So you can indeed see that we run this on Julia cluster, and each of those processes, each of those workers took a separate chunk of this job and executed it. Okay, so this works well if you do parameter sweep for evenly distributed workload, or if you know how to evenly distribute the workload. And now Julian is going to show us what's going to happen when you cannot distribute it so nicely. So, Julian, floor is yours. Yeah, I take my coffee, you bring your coffee,
Water.
and you take the second cup. Yours is longer.
All right.
And then,
All set. Okay. Thank you, Shemek. That was an excellent introduction to all forms of parallel computing that are built into Julia. So now, so my name is Julian Samaroo. I'm going to talk about Dagger, which is basically my project at MIT's Julia Lab. It's a new approach to parallel programming. Encompassing all of the various ways that one can do parallel programming on computing systems. We'll get into the details of what that means in a little bit. So first of all, there's just a little bit of setup we need to do. Get everything loaded. Some of this is going to look pretty familiar to what Shemek just showed you. Since this is a new notebook compared to the one that Shemek was working in, we need to add some more workers, and we're going to load our packages. Here we're going to be using Dagger, the focus of this talk, and also benchmark tools for benchmarking some of the things we're going to look at. And notice I'm using at everywhere. Sometimes when loading packages, you need to use at everywhere. Sometimes you don't. It's generally most safe to just use at everywhere when loading packages, just to be sure everything works correctly. So I just have a little snippet here that, everyone wants their code to go fast. It's always everyone's dream that, you'll write some code, you'll be, implementing some algorithm or something like that, or you're designing some framework, and you want it to just use all of the resources that the user's computer has available. Maybe they have a bunch of CPU threads, maybe they have some GPUs, maybe they have multiple servers, whatever, and you want your code to be able to use that. Of course, you want it to be fast and efficient and scalable. Unfortunately, the reality is this is very difficult to do effectively. You could certainly see some of this with the examples Shemek was showing, how there are different APIs for doing parallelism with different kinds of hardware and different modalities, and they don't necessarily fit together, and they don't necessarily always run as efficiently as you would hope. So I'm going to kind of run past this first part real quick, but just to give kind of just a real quick overview, what is Dagger? The purpose of this talk, it's basically a lot of things. It's a task runtime, it's a high performance scheduler, it's got a bunch of high level APIs, it's got all of these features, and basically it has all of this stuff because it's trying to solve a bunch of problems in parallel computing. Managing dependencies, abstracting computations over whatever resources you might have, whether they're multiple threads, servers, GPUs, whatever. As Shemek pointed out, Julia's built-in distributed library doesn't do load balancing, and Dagger does load balancing. It also, makes things run faster by doing tricks like latency hiding, and can automatically use GPUs. As Shemek pointed out, we are not going to cover GPUs today, but just wanted to point that out. So let's take a look at how to actually use Dagger. So basically, Dagger works pretty similarly to Julia's built-in green threading, multi-threading kind of approach. Really, everything comes down to tasks. And in Dagger, very similar to in Julia, when you do at async or threads.at spawn, or even the distributed at spawn at, Dagger tasks are asynchronous. So here, we're using this dagger.at spawn to basically say, okay, I want to do the operation 1 + 2, but I want to do this asynchronously. I want to kind of, create a task to run this in the background somewhere, and eventually I want to get the result of it.
If we take a look at the result of Dagger at spawn, we see it's this thing called eager thunk. Don't worry about the name. It's maybe not a great name, but it's basically a task handle. It's kind of similar to Julia's task object or the future object from at spawn at. It's reasonably similar. And, just like at spawn or something like that, you can call fetch to get its result, and that will wait for the task to finish and then say, okay, here's the result that it calculated. Now, in terms of just a little bit of, understanding what at spawn is really doing, it's basically a Julia macro that takes the plus function and takes the arguments, in this case 1 and 2, and wraps it in a Dagger task and calls it in the background asynchronously. Again, you don't have to worry about the name eager thunk, but just know when you see eager thunk in this following, in the rest of this notebook, it basically means a Dagger task. And also, if you are familiar with other languages, how they do kind of this form of asynchronous green threading or coroutines, this is typically called an async await style approach to parallelism, where you spawn some async task, and then you basically have a point at which you await the result of it. So just you might see this in Python or Rust or something like that. It's basically the same idea, but there are notable differences. So in Julia, we're working a lot. This entire week we've been looking at using functions. We've been using functions for everything, and so following that ethos in Dagger, really all Dagger tasks are based around a function call. So here. We're constructing a task around the function call plus with the arguments 1 and 2, but we can go further with this. So we can take the results of a function and pass them into another function, just like you'd expect, just like any other Julia code, you pass the result from one function into another. Importantly, though, when you construct a Dagger task from a function call, and then you pass that handle, that eager thunk handle, that's what A will be here, and we can just make sure we know that. Sorry, I need to add show A. When you pass one of these Dagger tasks to another Dagger task that you're spawning, Dagger will automatically handle kind of unwrapping these tasks. So A is not a number, right? We know 1 plus 2 is the number 3, but this is running asynchronously. A is not the number 3. It's some other object. Yet we're passing it here to this Dagger at spawn where we're doing 2 times A. So what is 2 times the task? That doesn't really, at first glance, it doesn't make sense. But if you kind of ignore the Dagger.at spawn part of it and just look at the operations we're doing, really what we're doing is we're saying A equals 1 plus 2, and then we're looking at 2 times A, and that's obvious, that's 6. That kind of bridge from Dagger task to Dagger task is handled by Dagger in the background. So you can basically kind of chain these together, pass the result from one Dagger task to another, and Dagger kind of handles all that for you and does all the things necessary to say, oh, okay, well, this task here depends on A, so we're going to wait on A, get its result, and then we'll multiply it by 2, and then, we get a result 6. So pretty straightforward. So importantly, Dagger executes your tasks in the order that is necessary. So, you can't do 2 times A before you've gotten the value of A. If you don't know what A is, you can't do 2 times A. So Dagger makes sure that it's executing things in order. Specifically, if you're interested, Dagger represents things as a directed acyclic graph. Basically a graph that doesn't have any cycles. It doesn't, there are no edges that cause the graph to form a cycle, and hence the name Dagger. Going a little bit more into a more involved example, say we wanted to create a bunch of Dagger tasks and have them kind of depend on each other to compute some final result. So say we're doing A is 1 plus 1, B is A times 2, et cetera, et cetera. You could just build up a bunch of tasks with Dagger and then fire them all off. And then at the very end, just fetch the result of the last one to get your final result. And some of the time we're waiting is just compilation time. If I were to run it again, it goes a little bit faster. But basically, all of those are running in the background, and Dagger is making sure that they execute in the correct order. So specifically in this above example, we can see that since B and C only depend on A, and D depends on B and C, well, basically what's going to happen here, based on this dependency graph, A can execute first, and then once A is done executing, both B can execute and C can execute, and D will be waiting. And then when both B and C are done, then D can execute. So Dagger makes sure to just keep track of this ordering. A very straightforward, obvious thing to do, but in fact, Julia's multi-threading and distributed computing libraries don't do this, even though most of the time you're needing to have some kind of synchronization and moving data around to make sure that you get stuff from one computation into another and get it all in the right order and make sure everything waits for other stuff to finish. And so Dagger kind of handles this for you automatically. You don't have to go to a lot of lengths to do locking and stuff like that and all that. Dagger makes that very easy. So what we don't see in this above example, because we're just doing really basic stuff, is that Dagger in the background is also using both multi-threading and distributed computing to execute these tasks. Now, we can kind of get an idea of what Dagger is doing by constructing just a slightly more involved function. Here we're creating this function called who am I? And basically what it's going to do, it's going to say, okay, which worker am I? Just like Shemek was showing in his part of the presentation, we're using myID to say which numerical worker am I? Am I 1, 2, 3, 4, etc.? And then we'll just kind of print hello from that worker. And now this is going to be, these next Dagger tasks that I'm going to spawn are a little bit more involved. You don't really have to worry too much about what specifically this scope thing means and how I'm kind of constructing this, but basically you can just read this as saying, this Dagger task right here, I want to run only on worker 1, this one only on worker 2, this one only on worker 3, and if I don't specify that, it can just run on any worker. So if we run this, what we'll see is that, okay, the first Dagger task says hello from worker 1, the second from 2, third from 3, and then this last one, in this case, said hello from worker 1, but if I rerun it again, it now says hi from worker 3. And if I keep rerunning this, you're going to get different results because it's possible to, basically by default, Dagger will just pick a place to run your code. It'll pick one of the workers in your cluster. If you just have, say a single laptop and no workers, and it'll just pick that one. But if you've got some other workers, say on your local system or in a cluster somewhere in Slurm, wherever, Dagger may pick to use that worker. And it'll go send all of the code over there, make sure it executes, and then get the result back. But basically, if you can also tell Dagger, hey, don't just pick one. I want you specifically to execute this task on this worker. And that's what we're doing here. That's all this is. Yeah, so one thing you might be thinking, okay, so if I run a task with Dagger, suddenly it's going to just execute wherever. It might go to some other worker. Well, isn't that kind of crazy? I mean, how do I know, how do I deal with all the data movement? How do I make sure all of my, data is where it needs to be and stuff like that? Well, instead of having to deal with all of those things, the idea of Dagger is that you don't deal with those. You let Dagger manage all of the data movement, all of the synchronization for you, and you basically just write your program with just the necessary dependencies that allow Dagger to know, okay, this thing has to go first, then this thing goes, and the data from this goes over to here, and et cetera, but you don't deal with the specific details of distributed computing and multi-threaded computing. Dagger handles those for you in the background. And, this goes beyond even to GPU computing. Again, we're not going to go into that, but it works all just the same, and you may not even notice that, say, you're using the GPU in the background. But again, we won't get into GPU computing. So anyway, let's get a little bit more information about what Dagger's doing. So aside from just using multiple workers, if your workers have multiple threads on each of them, in this case, our Jupyter Notebook process has, I think, 4 threads. And then we've spawned some other workers at the beginning of this presentation that each have 2 threads. Dagger will actually pick any thread on any worker when executing a task. So it's not just like Dagger will go over to, say, worker 2, but then always only use 1 thread. No, Dagger will see there are multiple threads on all of my workers, so I'm going to pick 1 thread on a worker and execute my task over there. So let's actually take a look at this and see how, see Dagger doing this. So here I'm slightly extending the who am I from above. We're still getting the worker ID. And then we're also going to get the thread ID. We're going to say which thread on whichever worker I am, which thread am I on, which am I executing on. And this will also be an integer, just like my ID. And then we're going to say hello from there. So if we run this, and here we're just going to run this 20 times, and we're just going to wait on all of them to finish. What we see is that, in fact, we're running tasks kind of all over the place. Worker 1, 2, 3, and multiple threads on all of them. So, we see that worker 1 has a bunch of threads and it's using those. And then workers 2 and 3 also have their threads, and Dagger is kind of spreading the load across those threads on all the workers. So, I mean, it's a little silly, but high performance computing is basically this. I mean, if you want, there's more involved, but basically with the simplest piece of code, with, what is this? 6 lines of code, you're easily running a bunch of tasks on a bunch of threads on a bunch of workers and having to do basically nothing. Dagger is doing all the work for you behind this statement. Dagger is spreading things around, doing work stealing, doing data movement, latency hiding, everything to make sure that this runs fast and this is distributed across all the resources that you have. That's pretty awesome. That's not something you can do with a lot of frameworks, including in languages like Python or Rust or Go or anything like that. It's generally not something that you see all kind of packaged together into one API. So that's why I believe that Dagger is really powerful for doing high performance computing, because it makes it so easy and makes it so straightforward. So let's get more into actually using Dagger to really do some real stuff. So let's define a function that does a little bit more. So this is a completely contrived example. I'm just making up a function which does something very expensive. It's inverting a bunch of arrays and multiplying them by some number I, and then summing up the results, and then returning, basically it's now constructing an array from this value total. It doesn't really matter, but the point is it's taking in a bunch of data, it's doing a bunch of stuff, and then it's returning a piece of data which is like kind of big, a matrix that's 100 by 100. This is, yes, that is a great point. This is kind of a thing to tell Julia to, I don't actually know if this is necessary anymore, but this is to make sure that Julia doesn't excessively compile a lot of things. So, this syntax right here is splatting. It's basically saying we can pass a bunch of arrays as positional arguments to this function. Well, Julia specializes code based on the number and the types of the arguments to a function. And in this next bit of code, we're going to pass differing numbers of arrays. So I don't want Julia to basically over compile and dominate our computation with compile time. Because really, even though this is expensive, it's going to be more expensive just to recompile this a bunch of times for a differing number of arrays. Exactly, right.
clapping.
Yeah. So, yes, but that is a good point. This is kind of an awkward thing that sometimes you may find you have to do. In this case, I do, but oftentimes you won't ever need to use something like that. So, okay, going back to the example, basically, this is a whole complicated lot of stuff, but all of this function here, create DAG, is basically saying, okay, let's make a really big DAG of array computations that are going to happen using our sum function here. We're going to make, we'll start off, we'll create one array, and then we'll spawn a bunch of Dagger tasks and pass that array in. And then we're going to do this a bunch of times, but each of these Dagger tasks is itself, if we take a look at sum function and we look here, we're generating an array as a thing that we're returning. So what's basically going to happen in this big loop is we're going to take in some number of arrays. We're going to create a bunch of Dagger tasks with those arrays. And then those are going to create some arrays, any number. In this case, it is n. So whatever we specify that to be. And then those arrays are then going to go into another round of creating Dagger tasks with those arrays that we just generated, et cetera, et cetera. It's basically just making a big directed acyclic graph just for the purpose of kind of getting an idea of like how long does it take Dagger to actually like execute code, given that it's able to exploit multi-threading and distributed computing. And we also have a branch which allows us to kind of compare against, well, what happens if we just run one task at a time, doing the exact same thing, but without Dagger, just one task at a time. So if we, for example, let's start off without using Dagger, and we're going to see basically how long this takes. So we had a little bit of compilation time. Let's run it again to get rid of that. So it took about 2.17 seconds. And now let's do the same thing, but with Dagger. We have some compilation time. And if we rerun again, we see that now it only took 1 second. Now, this is maybe not the speed up you'd hope for. This problem has some issues. The main issue is that when you do in Julia multi-threaded computing and you use BLOS, so basically linear algebra operations provided by the built-in BLOS library, BLOS does its own multi-threading, and that multi-threading, if you basically have a bunch of tasks executing on the same server that are all doing BLOS operations, they will reuse the same set of threads, and you won't necessarily get the performance or the speed up that you might hope. And also, this problem moves a lot of data around, which is expensive. So the speed up is not great, but it's still a 2x speed up in this case, or 50%. So we'll see some other examples as we go along. So yeah, basically that's as I explained it. So let's switch to a problem that's a little bit more heterogeneous. This problem was actually put together by Shemek when benchmarking Dagger, and there's basically this function called delay, and it is going to allocate some data, and then it's going to allocate a big vector of float64 values with 1 million elements. It's going to fill them with random values. It's going to take the standard deviation of that array. Thank you. And then we're going to do this for basically 660 times job size rounds. We're going to do it that many times. And then we're going to sum the results of those. Basically, it's another kind of problem that's also, it's a function that's kind of expensive. It allocates, but importantly, job size is an integer, so we're only taking in a really small value as an argument. And then sum is also just returning a float64, which again is very, very small. It doesn't take a lot of time to transfer. In comparison, to our sum function before, which is taking a bunch of arrays, which may be arbitrarily large, and then returning an array, which is a little bit bulky. So now if we take a look at how this goes, so if we just run this without Dagger, it will take a little bit. And what's happening here is, of course, for 15 times, we're basically calling this delay function with slightly different arguments. This is just some, this is the job size argument for each iteration. It's basically, it's arbitrary. There's going to be different values for job size for each call to delay here. And what we find is executing this in serial, it takes about 13 seconds. Okay. Now, if instead of executing this in serial, we executed this with Dagger, which allows us to use multi-threading and distributed, and we time that, it's going to execute way faster. And with compilation time, it was still, with 50% compilation time, it still only took about 2 seconds. If I run this again, the amount of time it'll take will approximately vary. In this case, it's taking a little bit longer. So one thing, Shemek, that actually was missed during the previous discussion with distributed is that this at time macro here, this does not show you compilation time on other workers. So if I do an at time here and it only reports 1.66% compilation time, yeah, this could be a lie because it doesn't know that other workers might be compiling code. It only knows that the worker it's on, which is this notebook Julia instance, it may be compiling some code, but it doesn't know that other workers are doing that. So it's usually important to rerun your code a few times just to kind of warm up all of the workers and all of their compilers to make sure that everything is compiled. But it's something you have to be careful about when you're doing any kind of distributed computing in Julia, because Julia is a dynamic language and we dynamically compile things when we see them. So you just have to be careful about that. So anyway, going back to this example, we see Dagger really smashes this problem in comparison to serial execution. So we're looking like we're about a little less than 6 times faster or so. Of course, these memory estimates are not accounting for the other workers. They're also making allocations. So you can't trust that. But the total runtime is significantly reduced. Now, I said at the very beginning, Dagger has a built-in high-performance scheduler. Well, unlike distributed, which does not have a scheduler, Dagger's scheduler is very good at what it does, and it's very good at packing work in together so that there is no wasted time, or there's very little wasted time when executing a bunch of Dagger tasks. So what we see here is, and this was previously generated when we put this code together, but this plot basically shows that on each of the threads that Dagger is working with, in this case, it just had 8 threads, Dagger packed the individual tasks together very efficiently. There's a very small amount of time in between each task. You see it's very thin. And for the most part, almost all the time, the threads are being fully utilized by one task at a time. And at the end, there's a little bit of inefficiency and, there's work to be done to improve that. But this is quite good. And this is hard to do if you were to attempt to roll your own scheduler. You would have a bad time trying to get this on a multi-threaded and distributed scheduler. It takes a good bit of work, and Dagger already has that for you. So if you want this, just use Dagger. Okay, now let's talk a little bit about data movement. So we've been previously looking at kind of computing and not worrying so much about like the data moving around and what's required to do that. So in Dagger automatically moves your data for you. And, as I've said, tasks can run anywhere, so their data has to go with them in order for the task to be able to do its job. Dagger handles this for you, and we're going to take a look at some of the kind of results of this, the implications. So I'm defining this time data transfer function, and it's going to do a few things. So first, it's going to do this kind of weird invocation. Basically, all it's saying is do this on worker 2, and it's going to spawn a Dagger task, which creates a big randomly initialized array. And we're just going to wait for that array to get created. So we're going to, I did neglect to mention this earlier, wait is kind of like fetch, but wait doesn't actually get the value of the Dagger task. It just makes sure the task is done executing, and that's all. So we're just making sure our array is generated from this invocation, and now we're going to use A. So first, we're going to take a look at we're going to use the data on the same worker that it was generated on, worker 2, and we're going to just do a sum of it using Dagger, and we'll fetch the results. And then we're also going to do an instance where we access this data, but on a different worker, worker 3, doing the exact same kind of thing though. And so if we run this and take a look at the performance, what we basically see, so what I'm doing here, so you'll see that I'm timing each of these instances here, where the first one I'm accessing the data on the same worker that the data's on, and in the second one, T remote, I'm accessing the data on a different worker. And I'm basically saying, how long does it take to access the data and do the computation on a different worker as compared to the worker that the data is on? And what we see is that we get a speed up when running this. I can actually run this again. And basically, we see that it takes 11 times longer to do the remote access as it takes to do the local access. So that's a great speed up. I mean, if you don't have to move data around, that's great. And that's exactly what Dagger does. Dagger knows that for this task here, it doesn't need to move A. A is already where it needs to be, so it won't. It'll just pass it right into the task and we're done. But for this task, we have to move the data to worker 3, make a copy of it, whatever we have to do, and it's going to do that, but it will take some time to do that. Yes, so the question is, in a distributed setting, is Dagger going to do a remote fetch in the background? And yes, that's exactly what it does. Dagger uses the distributed Julia standard library to do all this distributed computing, and it will do all the remote fetches for you that are necessary, so you don't have to worry about that. But you will see, of course, the performance implication if Dagger has to do that. So, of course, we don't want Dagger to move data around if unnecessary. I mean, it would be kind of silly if in the process of balancing a workload, Dagger suddenly assigned tasks to completely different workers than where their data is, and then had to go move all this data around across your cluster. I mean, that would be silly. You'd be waiting forever for data to move around with the slight hope that it may speed up your computation by balancing your workload. And so if you're not careful when designing a distributed multi-threaded computing system like Dagger and designing your scheduler, bad things like that will happen. Thankfully, Dagger is very smart and knows about all of this data transfer time versus, trying to spread your workload. And so Dagger will, when deciding, so basically okay, we're taking a look at a new function here, but basically what we're seeing is for these tasks, I'm telling Dagger, you must execute this on worker 3, or you must execute this on worker 2, right? But if we don't do that, we're giving Dagger license to execute tasks wherever it wants to. And what we basically want to see is we want to prove that Dagger will do the smart, efficient thing if it's given the license to do so. So this new function, what this is going to do, this is going to, again, construct some arrays, just like the last function. It's going to make an array A, an array B. We'll make sure that those are fully constructed. And A is going to be on worker 2, B is going to be on worker 3. Now, what we're going to do is we're going to tell Dagger, okay, I need to execute some function on A and some function on B 5 times each, but I'm not going to tell you where to execute it. I'm going to let you decide, Dagger. You can decide to execute it wherever you want. And we're going to, each of these instances, every time we spawn a Dagger task, we'll make sure to wait for it to make sure it's done. Basically, we're kind of doing these in serial just for explanatory purposes. And then the task we're doing is called where are my data, which is just basically going to say, okay, what array am I accessing? And just kind of computes the sum of it just for the sake of it. So if we execute this and then take a look at what happens, we see that every time we're accessing A, we always access it from worker 2, which is where A was allocated and where it resides. And every time we access B, we always access it from worker 3, where it was allocated. So this is a very obvious thing. If you as a person was told to act like a scheduler and given a bunch of tasks that will access some data, what's the first thing you're going to do? Well, if that data is really big that task needs, well, let me just assign that task to wherever that data is, because that's going to be faster. It's the obvious thing to do, and Dagger does that. Okay, so again, we can see that Dagger is doing, the intelligent thing. Now, what happens if there are conflicting priorities? So there's the case where, you don't want to put tasks on workers other than the ones where their data is. But there's also the point that we want to balance our workload. I mean, we can have maybe data all on one worker, maybe we allocated it all in one place, but then we still are going to, maybe we spawn a bunch of tasks. We may still want to move some of that data to make sure that we're kind of balancing our workload, even if we have to pay the cost of some data transfer. So what we're going to do in this example is define a function which accesses both A and B. So we're going to do the same setup as before. A is on worker 2, B is on worker 3, and we're going to spawn 10 tasks, but this time these tasks are going to access both A and B. And so the question will be, what decision does Dagger make? I mean, it's pulled equally in both directions for for worker 2 and worker 3 because of A and B being on different workers. So technically, both workers are actually an acceptable place to execute a task. So what does Dagger do in this case? Well, what we see is if we take a look at the workers that Dagger executes these tasks on, it's kind of going back and forth between 3 and 2, because it's, for the most part, equally a good idea to execute on 3 and 2. But of course, you don't want to load up all your tasks on just one worker. So what Dagger will do is say, okay, well, let me basically take these tasks and kind of split them between the workers. And it does it more intelligently than the way I'm describing it, of like, oh, well, I'll just take these 10 tasks and just kind of split them in half. In fact, it builds a cost model in the background, and it figures out the most optimal worker and thread to execute these things on. But for the most part, you don't have to worry about that. You can just assume I spawn a bunch of tasks, accessing data. Dagger will pick the best place to execute that task, given everything it knows. So that's very useful. So to us, this is obvious. This is what a human would probably do if given the task to or if given the job to assign these tasks to workers. But it is not easy to do if you're having to roll your own high performance computing library, or you're writing, you're implementing some algorithm that you want to use parallelism to execute to make it go fast, but you're now rolling your own scheduler and stuff like that, and having to do that because you want to get workload balancing, you want to get automatic data movement and stuff like that, and you'd have a lot of work to do if you're going to do this from scratch. Dagger is a complicated system, but it's rightly so a complicated system because doing all of this stuff is not easy. It requires a framework and a runtime and a system that is intelligent, that knows lots of things about what you, the user, are trying to do, and then knows how to exploit that information to make really good decisions. So basically, bottom line is don't roll your own, use Dagger. Dagger will make these good decisions for you, and all you have to do is provide your tasks and your data, and Dagger will do the rest. So, okay, this entire time we've really been looking at Dagger tasks kind of being used as is. We're going to move on for the rest of the presentation and look at the higher level APIs that Dagger provides. And to start with, we're going to look at arrays. So, in Julia, you will see arrays everywhere. They are a huge part of the language. They're built-in. They're used throughout Julia's runtime, compiler, many things. We use arrays for basically everything. Unfortunately, you will find that when you use arrays and you do things like, you call operations like sum or reduce or map, you'll find that actually they run single-threaded. There's no inherent parallelism to them. I can try to sum, I can do the sum of an array that's like, 8 gigabytes or 64 gigabytes. And guess what? It's going to run on a single thread. It'll use SIMD as Przemek was showing us, but it's not automatically multi-threaded, and that's kind of annoying, and it's not automatically distributed. So you're not going to benefit from the multiple servers you might have configured. And that's kind of unfortunate. And maybe over time this will change, but it's going to be a very slow process. Making big changes like those to an existing language is it's not easy. It takes a while. Thankfully, we can take a look at just to kind of give us an idea of what it would look like to do this on your own before we get to how Dagger does this. We can take a look at doing this ourselves. So we can, for example, make a multi-threaded version of the sum operation. So Przemek was showing us a few ways to do this before. So I just kind of have my own implementation that I put together. And we can kind of take a look at how this works. Basically, empty sum, it takes an array that we want to summate, and it's going to do the same thing that Julia's threads.atThreads or @distributed does. It's basically going to say, okay, the array is however big, and we're gonna split it based on the number of threads that we have. So if we have 4 threads, we're going to split this array into 4 approximately even pieces. And then what we're going to do, we're going to use the threads.atSpawn operator and some reduction buffers that we allocate to basically say, okay, well, take a partition of A and on each thread, do a sum and then store it into our reducer bucket. And then at the end, we wait for all of those. And then when we're done, we return the sum of all of those reduction buckets. Very straightforward. This is, basically a pretty naive way to do a multi-threaded sum, but it's pretty effective in this run here. So here, we're allocating some big array. We make sure that the Julia built-in sum gives the same result as our multi-threaded sum. And if we were to actually time these and look at them, the single-threaded sum takes about 100 milliseconds, but the multi-threaded sum only takes 40 milliseconds and just allocates a little bit of memory for these reduction buckets. And so that's great. That's nice and useful. But of course, this required us to do quite some work to put this together just to get a multi-threaded sum operation. And of course, this only supports multi-threading, doesn't support distributed. You can do distributed. It's not too difficult. As Przemek was showing us before, we have the PMAP operator, which is a parallel map, and it basically lets you do what you'd expect. Here, we're, again, just partitioning A, but this time based on the number of workers that we have. And then we basically ask PMAP, okay, do a sum on each of those chunks. And then when that's done, we'll take the sum of all of those sums to get the final value. And if we are to time this, this time using a slightly smaller array, I don't want to run out of memory. Distributed computing, unfortunately, tends to allocate a lot of memory. If we are to time this, we first, of course, made sure that our distributed sum gives us the right result. And then if we time this, we see that with a single worker, this takes about 750 nanoseconds, pretty good. And then multi-worker, it takes 206 microseconds. So that's pretty horrible. It also allocates a lot of memory. That's pretty unfortunate. But on the plus side, we did execute it in a distributed manner. And maybe if the array was bigger, it would be faster. But, you know, it's not guaranteed. But we were able to at least execute this in a distributed manner. And of course, this only was distributed. So even though we have multiple threads on each of our workers that we've created, it's only using one thread from each worker. And that's kind of unfortunate. Now, of course, we can roll our own implementation that uses both. It's a little bit more of a pain. We basically have our MT_sum function before, where we do a multi-threaded sum, but then we wrap that, we call that in basically the same as our dist_sum function above. And so we basically say, okay, on the outside, break up this array into, say, 3 or 4 pieces, and then each of those pieces we then break up into a further set of pieces that multiple threads on each worker will kind of sum and reduce. So, and this is basically combining multi-threading and distributed together into one summation function. Now, if we're to run this takes a little bit. This will hopefully not run out of memory because, again, we are using multi-threading and it does allocate quite some excess amounts of memory. And if we run this, we see that, okay, for a slightly bigger array, it takes about 100 milliseconds. And now we're waiting for the our multi-threaded distributed loop to run. And in this case, it was not too great. And that kind of sucks. So it took less time for a single thread on a single worker to do the summation. And for multiple workers with multiple threads, it still took 10 times longer and allocated a bunch of memory. So that kind of sucks. Yeah. So this is the communication. Exactly right, Shemek. So the problem is that in the process of doing this PMAP, PMAP had to distribute the chunks of A to all of the workers, and that is unfortunate. It would be nice if instead A was already distributed and our threads on our multiple workers could just each work on some local data and then just communicate back when they're done. But, this is the easiest implementation that one could really put together, and it doesn't have support for things like that. So what if we want to do better? So thankfully, Dagger has an answer to this problem. It is called the D array or Dagger array, distributed array, whatever you want to call it. It's called a D array. And it basically does what I've described, so what I've described is we want to, instead of allocating an array on one place and then distributing it out and then doing our sums and bringing those together, instead, you can allocate an array as a set of chunks automatically on multiple workers at creation. So let's be a little bit more concrete. Say we want to create a random array that's distributed with chunks of size 1024 by 1024. And in total, it's 100 times bigger than that. The total array is 10,240 by 10,240, and again, split into these chunks. You can construct a Dagger D array by basically doing this line here, which says, okay, create a random array, just like normal Julia Rand, but we pass this thing called blocks, which basically says, okay, instead of just allocating the array here on whatever worker, whatever Julia process I'm on right now, instead allocate it in a distributed manner by partitioning it into blocks of size 1024 by 1024. and basically allocate it like that. Create a bunch of partitions across our workers in a distributed manner, but treat them as one big array. And that's what we're doing here. And then we're using fetch to kind of get the result of that. And what we'll see, so let's actually take a look at what this is. So, so it'll take a little bit while it compiles, but what we can see is DA is this Dagger D array. And it's just like a regular Julia array, but it is a automatically distributed array implementation. Conveniently, just like any Julia array, it has support for many of the built-in functions you'd expect, like sum. I can calculate the sum of a D array, and you know, it takes some amount of time. It makes a bunch of allocations, but basically this here that we've done is a distributed and multi-threaded sum. So it looks like just regular Julia sum. It works, you know, it will give you the same results as we check down here, but it is automatically distributed and multi-threaded through Dagger. So the Dagger D array basically uses Dagger tasks under the hood to operate on all of these partitions of this random array that we created up here. And you know, you don't really see this. The API is simple. I create an array, it happens to be distributed, and I call the sum on it. And I don't really care what it's doing in the background, but I get the right result, and it's pretty quick. Of course, performance is not as amazing as I might like, but it's still pretty good for not really having to do any work. You just allocate the array and then call sum, and that's it. So that's pretty convenient. Now you'll notice, of course, that we had to use this fetch function here. So just like working with Dagger tasks, things are asynchronous in Dagger. So oftentimes you need to use fetch or wait to kind of do synchronization and make sure things are complete. So one slight difference with Dagger tasks is that fetch on a D array operation like this returns a D array. And then if you actually want to get the result as just a regular Julia array, you instead call collect. And this is consistent with how Julia's other array implementations work. If you call collect on some weird kind of array, say a GPU array, you'll get back a regular CPU array like you can like you're used to working with. So moving on, the Dagger D array supports a variety of array operations. Another way we can actually construct a D array real quick is we can actually just allocate a regular array, just a standard Julia array, and then distribute it. Here, taking a 64 by 64 matrix and splitting it into partitions of 16 by 16 with Dagger's distribute function. And now we have a D array. And now we can say, okay, let's do, say, a map operation. So say we want to operate on each element of the D array. We can pass it to the map function. It works just like, for example, this is the same idea as... Yeah, exactly. So this is a behind the scenes doing a Dagger operation, but it looks just the same as doing the standard Julia map that's not distributed or multi-threaded in any way.
So via multiple dispatch, Dagger is providing implementations for the methods in Julia.
Right. So just to repeat, by using multiple dispatch, Dagger basically overloads a lot of these methods and works just like how Julia works, provides kind of the same semantics, but does so in an automatically parallelized manner. Sorry? Yes, so to repeat, the question is this Dagger underneath? And yes, so under this operation, because DA is a Dagger D array, then this operation under the hood is using Dagger, using the regular Dagger.at_spawn macro that we were seeing at the beginning of this presentation to do a multi-threaded distributed map operation. And Oh, yes. So, yes. And just, so the question is distribute has a fetch under the hood. So, I believe DA, yes, DA is, excuse me, distribute has a built-in fetch that it does. Some things are slightly inconsistent. It's kind of a work in progress to kind of even out some of these weird edges. But distribute kind of does the distribution and then gives you back a D array. So it's kind of already, it's not necessarily done distributing the array, but it does give you back a D array object. So actually, it may not be a full fetch.
It would be nice to show like methods with the array and see how much has already been implemented.
I think I'm not sure if we'll be able to do that, but let's try. Let's see what we can do here.
It's methods with.
Methods with D array. And then I think we need to say Dagger dot D array. And let's see. And methods with is just telling us which methods are defined for the D array. Yeah, most of these are not really useful to users. Collect, fetch, and similar are useful. The reason for this, the reason why you don't see things like sum and map and stuff like that is that when we do,
I think methods with maybe takes the package name. If you want to search outside of the package, I think it has some parameters identified.
It may be that it's methods with not showing us this, but also part of it is that that probably is what it is.
I forgot the name of the package.
Yeah. And we can see if
question mark with method with.
Take a look at this.
Oh.
So it takes the type and then the modular function. Okay, so we can say Dagger.d array, and then we want to say it should be base. Should be defined on base. And no, we don't see them. And that's okay. The way that some of these things are defined, they're
By super types.
yes, via super types. It is this array op. Yep, there we go. There's the rest of our methods. Yeah, the Dagger D array is a subtype of array. Right. So, okay. And so we'll move on past that. So yeah, so we can see there's some operations like transpose, sum, prod, reduce. There's our map implementation is equal, stuff like that, all useful things. And there's more that we need to implement, but this is a basic set of useful functionality. Another useful set of functionality that is super helpful is broadcasting. So we can take D arrays like DA and DB and do a more complex broadcasting operation on it.
Kind of distributed broadcasting.
This is a distributed. Yes, this is a distributed multi-threaded broadcast implementation that fuses the plus and the multiply operations automatically.
In a distributed manner.
In a distributed manner. So yes, this is quite powerful. And when, and basically Dagger is doing all the data management behind the scenes. And also this broadcast, Julia's broadcasting is doing some useful fusion to make sure that, well, for each chunk or partition of DA and DB, we take those together and then multiply A by 2 and then add B to it. And we do this in parallel for all of these partitions. So each partition in DA and DB they're basically being paired up. And then we're creating this large number of pairs, and Dagger is then executing those as tasks to do these lower level broadcasting operations, to do the actual operation on each pair of partitions. So that's quite powerful. And all you do as the user is you just write the broadcasting operation. And if you want to see the result, you call collect to turn it into a regular Julia array. Now I've been saying that this stuff is multi-threaded and distributed, and it is quite useful to actually prove this just for the purpose of feeling a little bit confident about that and making sure we know that that's the case. So what we can do is we can basically say, okay, let's create a randomly initialized array. It doesn't matter what it is. And let's say now, okay, for each element in DC, this Dagger D array, we're going to instead switch that element to be the worker ID that our task is running on when we do a map operation. So when we're doing a map on a Dagger D array, what worker was used to execute that? And we can basically take a look at the resulting array to say, okay, well, what was the data distribution? What was the work distribution? How did Dagger spread the computation? And if we look at the result, we see these kind of 4x4 partitions with each all the same workers. So here, this partition here was computed on worker 1. This one was on worker 3. This was on worker 1. This was on worker 2. So the question is this a random layout? So the reasoning you see this 4x4 is that this array DC is 16 by 16 total. As you can see, that's a row of 16 and then a column of 16, but each of the partitions are 4x4 partitions, and each partition is its own unit. So when I'm going to, say what worker is working on the first partition, well, all elements in the first partition are going to execute on the first worker because that's all processed at once on that one worker in a single Dagger task.
Selected that let's say top right corner and on tools. Was this second worker selected randomly, or there is some way how it's being chosen, like 1 to 3, 1 to 3, and so on?
Great question. The question is, are these assignments selected randomly, or is there kind of a pattern to this? So to an extent, it is random. But what happens is that as Dagger goes through basically assigning the tasks that get generated to compute this map operation, as it goes through and determines which worker and which thread on each worker to execute a task on, Dagger is looking at what it's already assigned. And then, so if it says, okay, this first partition, I'm going to execute on worker 1. Well, when it goes to look at this second partition here, well, worker 1's already busy. So it's going to take this next partition and put it on worker 3. And then this next one, well, it decided to put it on worker 1, but then the one following that, worker 2. For the most part, we see that this work distribution is approximately even. We've got 1, 2, 3, 4, 5, 6, 7 of our partitions execute on worker 1. 1, 2, 3, 4, 5 of them on worker 3. And then 1, 2, 3, 4 are on worker 2. One piece of information I forgot to also point out, our partitions already exist on a given worker. A partition is on some worker. And so potentially when deciding where to put, say, this first partition, it's likely that that partition already existed on worker 1. And so Dagger was just like, okay, well, let me run this task on worker 1 where that data is. Same for this next one, same for the one following. It's technically, it's not guaranteed that that's going to happen. You can't guarantee that just because a partition of a D array is on a given worker that a task will execute there. And that's okay because you don't want that to be guaranteed, because it may be that that worker where that partition exists is actually super busy. It's got a lot of tasks running on it. Previous user code has already assigned a lot of work to it, and it's busy working through a big queue of stuff to do. Well, you don't want to keep assigning more work to it. That's silly. If workers 2 and 3 are just sitting there doing nothing, well, in that case, it may be better to move those partitions over to workers 2 and 3 and run the jobs there. So it's kind of a mix of where is my data and how busy are my computing resources, and Dagger handles that for you in the background. You don't have to deal with this, but you can see the end result of this by kind of taking a look at this. So the question is, are there different kinds of data distributions? So the Dagger's D array The only currently supported data distribution is these regularly sized blocks. However, there's no restriction on that long term. The plan is to add a variety of different kinds of data distributions. Of course, you can always pick any kind of rectangular shape for your partitions. But in terms of considering kind of irregular block patterns, if you know, for example, that certain parts of your matrix are more likely to be accessed together than others in kind of an irregular manner, the plan long term is to support different partitioning strategies and potentially user-defined strategies where you can tell Dagger, hey, this is actually how I want you to partition this array or create it. And then Dagger will respect that. So long term, that is something that we plan to add, but it is not a feature that we have today. Great question. So moving on, we can take a look at the threads being used as well. We see basically the same idea. Note that the 2 here is not necessarily the same thread as the 2 here. They may be on different workers. We just don't see that here. In fact, well, it'll be kind of hard to render both the worker and the thread, but we can see that generally in terms of the worker domain and the thread domain, things are pretty evenly distributed. Spread. Okay, so how does the D array work? I mean, I've said that it builds on top of Dagger, but is it a special built-in? Is it like using some special Dagger internal only things that you as a user are not allowed to use? No. The D array could be pulled out into its own completely independent package. It depends on Dagger's public API, and that is it. So I can actually prove this by basically showing, well, what is inside a D array? Well, inside a D array, there's this field called chunks. And basically all that is just a matrix of our partitions. They are lazy references to our partitions. As we saw before, what does this mean? This eager thunk thing is a Dagger task. So for each of our partitions in our 16 by 16 partitioned into 4 by 4 D array, we basically see for each partition, we have a Dagger task associated with that partition. And what that basically means is that Dagger's D array is just a container around a bunch of Dagger tasks or lazy references to data. That's all it is. There's some extra stuff in there to make sure that you can do regular array operations, but that's really it. You could write your own D array implementation on top of Dagger's public API, and it would probably look like this. And so we can, take a look at, say, like, what does one of these partitions actually look like? Well, we just fetch it, say the partition at index 3 by 4, and we see it's just a regular Julia, right? It probably exists on a different worker. In fact, we can take a look at that real quick. We can say, well, it's a little bit tough to actually show that with Dagger tasks, but what I should be able to do is say my ID to get a general idea of where is this partition. Give me just a second. Dagger. I'm going to do a slightly different approach to this. 1 moment. Live coding during presentations is rarely a good idea, but we're going to try it anyway because it's worthwhile. So let's see where this partition is. This one is on worker 1, and this one's on worker 3. This one's on worker 1. So basically, these partitions are spread about, and we can see that. And so anyway, the underlying D array representation is pretty simple. It's just a big bunch of Dagger tasks that represent all the partitions. We are running out of time.
7 minutes.
Okay, 7 minutes. So I'm going to speed through this kind of quickly. A variety of operations exist on the D array. You can reshape it. You can do a matrix multiply. Super straightforward. You can do sorting on the D array. If it's a one-dimensional D array, then you can sort it just fine. And that, of course, executes distributed in parallel, blah, blah, blah. I keep saying this. That's the pattern. we've looked at arrays, but a lot of this week's presentations have been about tabular programming using data frames. Dagger also has a data frame distributed multi-threaded implementation called the D table. Now I'm going to just kind of skip through some of this initial setup, and I'm not going to evaluate these cells because we don't have so much time to wait on them. But basically, the D tables package provides a D table object, which is a Dagger table, and it basically wraps a bunch of regular Julia table objects, like a data frame or a CSV file or some table objects like that. And it basically virtually concatenates them row to row. So basically you can have one data frame that's say 1,000 rows on top of another data frame that's 1,000 rows, et cetera, and all of those together, each of those is a partition, and all of those together create a D table, a partition table essentially. So super simple to create. I can take an existing data frame, wrap it with the D table call, and then pass this argument here, which I'll explain in just a second, and we get a D table with 39 partitions. Cool. What is this? This is the chunk size. This is like that blocks operator that I showed for the D array. But instead for the D table, it's basically saying how big is each partition? What is the so-called chunk size of each partition? And it's saying, okay, we choose each partition to be 1,000 big. And so because DF3 is about 39,000 large, well, okay, so we're going to get 39 partitions to store all of those individual partitions of tables. That's pretty straightforward. And just like a data frame, you can do various operations. You can select columns from it. You can use fetch to turn it back into a single data frame, and then do regular data frame operations on that, of course. You can, there are built-ins like reduce and group by, so you can do a lot of the standard data analysis, data processing things you might expect to be able to do. And in this case, again, we're converting back to a data frame just to kind of be able to render our results. Now this all is kind of annoying. There's like a lot of stuff required to kind of show these results. This will improve over time, but oftentimes you'll need to call fetch or data frame or similar to just get the data into a single server representation, like a data frame or something like that. Because of course the D table, like the D array, like the rest of Dagger, is asynchronous. And then of course, as you'd expect, we have join operations, we have left join, right join, inner join, etc. And that all works fine. It's of course automatically distributed, multi-threaded, blah, blah, blah. I keep saying that. I'm not going to prove that right now, but you can take a look at the source code if you want to prove it to yourself. And it all just works automatically. Of course, you need to use fetch to make sure things have actually finally completed. And just like the D array, the D table is built on top of regular Dagger tasks. It's just a container where that container holds a bunch of Dagger tasks where each task pertains to a given partition. And that's it. We can take a look at one of those partitions. We see it's actually just a regular Julia data frame. Super simple. And then the D table kind of virtually concatenates those together. So kind of cool. And basically that's it. So just as a final point, Dagger is of course super powerful, but one thing which is a work in progress is our high-level APIs, our D array, our D table, and the upcoming D graph for graph analysis. They have some operations defined. Not everything is defined, but adding those, each operation is a small amount of work, and then you get all of your parallelism for free. And so that's pretty convenient, but as a project, we have a little bit of a way to go before we start covering more and more operations that users expect. But something I didn't really show here today is that if the D array or D table supports all the operations that you need, you can often pass them into generic Julia code that works on arrays or tables, and the D table will work automatically. It tries to match the existing APIs that the rest of the ecosystem uses for regular arrays or regular data frames. And so you can do generic programming with this asynchronous, highly parallel API without even really knowing that you're doing that. So, which is kind of cool. Yeah, so that is it for this presentation, but thank you so much for listening in.
Okay, thank you.
All right.
Yeah.
Thank you.
So,
And
it was the last lecture, workshop, so thank you. Everybody, we survived to the end. So,
and
I
then,
think we can stop recording.
yep. Okay. Very good.